Good morning, students. Good morning. Okay, day by day, attendance is going down, right? Okay. So, we were talking about basic concepts of organic chemistry, right? 1 minute. Okay. So, with respect to yesterday's class, can any one of you send me what we have discussed in the yesterday's class? Can any one of you can send me what we have discussed in the last class? So please inform to your friends to attend the live class so that if they have any question or doubts, they can raise it. Okay, now? So positive and negative resonance. Yes, very good. So we have discussed about positive and negative resonance. Yes, we have discussed about the positive and negative resonance. So what do you mean by positive resonance? Where electrons from the substituent, it will flow towards the ring. Okay, so that's where it is called as positive resonance. So where electrons will be moving away from the substituents, or I can tell that electron donating groups. Electron donating groups. So that's where whenever these type of substituents are there, they will show the positive resonance, where electrons will be pushed towards the ring structure. Okay. So which are those examples? Examples can be chlorobenzene or any of the halogens. Chlorobenzene, or it can be phenols. It can be phenols. Then anything else we have discussed, that is benzenamine. That is aminobenzene. Aminobenzene. So that's where we have some of the example. So first one, chlorine as a suffix, prefix. So therefore chlorobenzene. Then here OH group. So therefore we can directly call it as benzenol or phenol. Okay. Now here we can call it as benzenamine. We can call it as benzenamine or aminobenzene. But benzenamine will be the proper one because amine, it will be used as a suffix, not as a prefix. So that's where we have the examples for positive resonance showing elements, where chlorine will push the electrons. In all these cases, electrons will be moving towards the ring structure. Okay, therefore it is called as positive resonance. Therefore it can be called as positive resonance. Right? Okay, screen is foggy. 1 minute. 1 minute. Maya, screen is foggy. 1 minute. So what about now? Whether it's clear? Here it looks fine. Now whether it's clear? You told screen is foggy, right? Now whether it's clear? Okay. Yeah. Is it clear? They are telling now it's clear. Okay. Okay. So that's what I was telling. These are some of the examples for positive resonance. Chlorobenzene or phenol or aminobenzene. Okay? Yes, fine. Rohan. So that's where we have the positive resonance. Now when I am talking about negative resonance, where we have the electron withdrawing groups. So electron donating groups and electron withdrawing groups. So that's where we can tell it as electron withdrawing groups. Okay. So in this case, what will happen here is electrons will be moving towards the substituent. Here it is moving away from the substituents. Here electrons will be moving towards the substituents. That's where we have the, yes, Gauri, movement of electron away from the benzene ring. Yes, absolutely correct. So that's where one of the example can be nitrobenzene. One of the example can be nitrobenzene, right? Where electron is moving towards the substitutes. Fine. So directly we have another example for this one is benzoic acid. Another example can be benzoic acid. Okay. Same way we have benzaldehyde. Same way we have benzaldehyde. Benzaldehyde. Okay, na? So like that, electrons will be moving towards the substituent. Please remember, whatever arrow I have shown, it is just to make you understand. It's not compulsory. No need to write these arrows and all. So I have written that one to make you understand. Okay, another one we can write it here is toluene. With respect to negative positive resonance, we can go with toluene also. So where electrons will be moving towards the ring structure. So methyl benzene, or we can call it as toluene. So any alkyl group attached, they will be acting as a electron donating groups. Okay. So that's where we can have the positive and negative resonance. That's where we can have the positive and negative resonance. Okay. So all of you have understood. So this is what we have discussed. Now, when it comes to organic chemistry, when it comes to chemical reaction, it is just with respect to nucleophiles or electrophiles and a given organic compound. How they are going to interact. That's where we have the basics with respect to reactions, organic reactions. Now, all of us we know that when I am talking about a molecule where a substituent is electron donating group, so I will take the help of chlorobenzene. Now, all of us we know that since electron is moving towards the ring structure, electron density will be more at the ortho and para position. So this is ortho position, this is also ortho position, and this is para position. So that's where electron density will be more. So while in those positions electron density will be more, that's what we have discussed. Due to the resonance, all of us we have observed that whenever electrons will be moving across the ring structure, there will be formation of electron density at these particular regions. During resonance, when we are writing the structure, we have come across. Once it will be here, then it will come here, then it will come here. So therefore, overall, electron density will be more at ortho position and at para position. When we have a condition where positive resonance is going on, and naturally at meta position, no electron density. At meta position, no electron density. Right? So that's what we can observe when it comes to positive resonance. Now naturally, when I'm talking about electrophiles, so when I'm talking about electrophiles, they will attack ortho or para position. They will attack either ortho or para positions, right? So that's where positive resonance, whenever it is there, in those conditions they will be ortho or para directing with respect to electrophiles, because electrophiles are electron deficient species. So they are going to attack those regions where electron density is more. Now exactly opposite when it comes to nucleophiles. So with respect to nucleophiles, they will attack where electron density is not high. So that is with respect to meta positions. So with respect to nucleophiles, it will be meta directing. With respect to nucleophiles, it will be meta directing. And with respect to electrophiles, it will be ortho and para directing. Now please remember that when it comes to IUPAC nomenclature, we are not going to use the word ortho and para. You have to remember this one. Ortho, para, meta and all, we are not going to use when we are dealing with the IUPAC nomenclature. In IUPAC nomenclature, we are going with the numbers 1, 2, 3, 4, 5, 6 like that. So this will not be utilized. Okay, but when we are talking in general, then we can tell that this is ortho position, this is para position, and this is meta positions. But in IUPAC, no, it will be considered as position number 2. Since it is 1, it is 2, 3, 4, 5, 6. When it comes to IUPAC, no ortho and para, it will be numbering. All of you got my point? So this is with respect to those compounds where there is a presence of positive resonance, where there is a presence of the positive resonance. Okay, so then we have another condition, as we know, that is with respect to negative resonance. I will take the help of nitrobenzene, where electron is moving towards the substrates. Where electron is moving towards the substrates. Now what will happen? Since electrons are moving away from the ring structure, it will gain the, or electron density will be less at ortho and para positions. Electron density will be less at ortho and para positions. So that's what we can indicate that one by positive sign. We can indicate that one by the positive sign. So naturally, when we are talking about electrophiles, when we are dealing with the electrophiles, so they will not move towards those positions where already electron density is less. Because electrophiles are those species which are having deficiency of electrons. All of you have understood? So therefore, they are not going to attack those regions which are already deficient of electrons. So therefore, they are going to attack those regions where deficiency of electron is not there. Okay, so that's where electrophiles, they are going to attack meta positions. They are going to attack the meta positions. All of you have understood? So therefore, when it comes to electrophiles, in case of the negative resonance, they will be meta-directing. They will be meta-directing. But if I take nucleophiles, electron-rich species, now they are going to attack those positions where electron deficiency is there. Where electron deficiency is there. So therefore, when it comes to nucleophiles, they will be ortho and para directing. They will be ortho and para directing with respect to those compounds where we have the negative resonance. All of you have got my point? So this is an example for negative resonance. Why they are showing negative resonance? Because electron withdrawing groups are present. And when it comes to here, it will be with respect to positive resonance. Why it is positive resonance? Because electron donating groups are present. This is what we have discussed. Okay. So any doubts in this? Any doubts with respect to these concepts? Because they are all very important for your examination point of view. Means with respect to competitive exam, or if you want to understand the organic chemistry, reactions and all, these are all fundamentals. Okay. Okay. So now in that case, we will move to next. That is called as inductive effect. That is nothing but inductive effect. Okay, na? So that's where we have the inductive effect. Now, what do you mean by inductive effect? So that is nothing but displacement of electrons. Inductive effect is nothing but displacement of electrons. Displacement of electron. Okay, na? So due to the presence of substituents, so that's where we have the inductive effect. So for this test, they might have informed, right, Ashish? Or I will let you know. For this test, they might have put it in the group, or I will inform it. No problem. Okay? Fine. So that's where we have the inductive effect. Now when it comes to resonance, in resonance also there will be displacement of electron or movement of electron. But that will be due to conjugated double bonds. That is due to the conjugated double bonds. But here it is nothing but there is no question of double bonds and all, but there will be displacement of electrons which is due to the presence of the substituents. And all of us we know substituents can be either electron withdrawing substituents or they can be electron donating groups. Right? That's what we have seen just before when it comes to resonance, positive and negative resonance. That's where we have the electron withdrawing groups or electron donating groups. These can be the substituents. Okay, whether I am clear? So in that case, we have one of the acid, that is HCl. So why HCl is considered as a acid? That is because they are going to release the H plus. So that's where we have the HCl. Okay. Now, if I take sulfuric acid, even sulfuric acid will be considered as a strong acid. Why? Because they are going to donate the H plus. Whether I take HCl, they are going to form the H plus in the water. If I take sulfuric acid, they are going to form the H plus in the water. What's my point? Yes, Rohan. They will give or they will donate H plus. So therefore, they are considered as acids. And now, to be more appropriate, I can call them as strong acids. Because they are going to completely dissociate. So what I mean to tell here is, if I take 10 molecules of HCl, in the product also we have the 10 H plus ions and 10 chloride ions. Now same logic. If I take 10 sulfuric acid, in the product we have 10 H plus and 10 bisulfate ions. HSO4 minus means bisulfate ions. So that's where we have the strong acids. So why they are called as strong acids? Anyway, these things in detail you are going to study in a topic called as chemical equilibrium. Okay, but for time being you should understand that they are called as strong acids because they are completely getting dissociated in water. Okay, so there is no question of any HCl will be left over. It will be completely dissociated. They are the good donors of H plus. This much is clear. So this is what this arrow indicates. This is one way. It's only towards right side direction. So there is no back side direction. Backward is not there. Only forward is there. All of you have understood? Any doubts? Oh. So that's where we have the strong acid. But I have a condition. I have an acid which is also commonly used even in day-to-day life like vinegar and all. Right? So that is acetic acid. Are they reducing agents? Yes, we can consider, but since H plus is there, they can take up the electrons. So we can consider them as a Lewis acids also. We can consider them as a Lewis acids also, since H plus is getting released. Okay. Now, if I consider acetic acid, which is the component of the vinegar, 4% acetic acid is nothing but vinegar. All of us we know vinegar, it is commonly used in the kitchens, right? So now when I'm talking about acetic acid, now the formula here is CH3COOH. Okay, so which is also called as ethanoic acid. Which is also called as ethanoic acid. Okay, acetic acid is a common name, but ethanoic acid is a IUPAC name. Okay, na? Now, if I take this particular molecule, acetic acid, now even they are going to be dissociated. Even they are going to be dissociated as CH3COO minus and H plus. Okay, so that's where we have the carboxylic acid. That's where we have the carboxylic acid. Why they are called as acid? Because they can release the H plus and itself it will become carboxylate. It will become carboxylate. All of you have understood? So, carboxylic acid. Ic acid means there is a presence of H. They are not dissociated. But when I am telling ATE, 8, that means there is a H plus is dissociated. They are in dissociated form. So, carboxylic acid, carboxylate. So, therefore, carboxylic acid is a acidic functional group. We have two functional groups which are acidic in nature. One is sulfuric acid and another one is carboxylic acid. All of you got my point? So that's where we have carboxylic acid which will become carboxylate once they dissociate the H plus. Same logic. Ethanoic acid which will be dissociated. Ethanoic acid is also called as acetic acid. So which will be dissociated. Now we can call it as ethanoate or acetate or acetate. So here acetic acid. Ethanoic acid will become ethanoate or acetate. Naturally, when I am telling ethanoate or acetate, it's understood that they are negatively charged molecules. Okay. Now another product is H plus. So what you can observe here? What is that compared to earlier one where we have discussed about HCl and all? What is that we can observe over here? Anyone? What you can observe over here compared to HCl and sulfuric acid? One thing is sure, in both the cases, they are releasing the H plus. HCl is also giving H plus. Sulfuric acid is also giving H plus. Even acetic acid also releasing the H plus. But anything else you can observe? Anything else you can observe here? In both the cases, H plus will be released into the solution, no doubt. But something we can observe which differs from the earlier case. Anyone? Huh? Okay. So I will write HCl also here. Now I have written HCl also. Okay. Rohan is telling this has a carbon. Yes, of course. This is an organic acid. This is a mineral acid. Cl is not a organic acid. Yes. That is one thing. Very good. Anything else? With respect to reactions, I am telling. As a molecule, yes, as Rohan told, acetic acid is an organic acid, a carboxylic acid containing molecule. But when it comes to HCl, it's a mineral acid. It's not an organic acid. There is no carbon in its structure. That is one thing. Fine. As a molecule, this is the difference. But as a reaction, anything? So what we can observe here is, when it comes to acetic acid, for its dissociation, you can see the arrow, and when it comes to HCl, you can observe the arrow. Right? So that's what we can see the difference. Yes, Shashank, very good. In case of the HCl, it is in the one direction, but in case of the acetic acid, slightly it will be in one direction, but more towards the other direction. Okay. So anyway, these things you are going to study in your chemical group. Yeah. But for time being, you can understand that by this we can tell that acetic acid is not going to completely dissociate. So what I mean to tell you is, if I take 10 molecules of acetic acid, 10 molecules of acetic acid, in that only 2 will become acetate and 2 will be H plus. So what is leftover acetic acid? Leftover acetic acid will be still 8. Okay. So what I mean to tell you is, unlike HCl and sulfuric acid, where they were completely dissociated, but in this case, acetic acid is not going to completely dissociate. Only few molecules of acetic acid will get converted into acetate ion. But many of them, they will remain as acetic acid. That's what this arrow, long arrow, this is small arrow. Okay? All of you have understood? So that's why I can call acetic acid is a weak acid in water. Acetic acid as a weak acid in water. HCl, when I will add it to the water, they will completely dissociate. Sulfuric acid, when I will add it to the water, they will completely dissociate. But when I am taking acetic acid, if I add it to the water, they will not completely dissociate. So many of them in their undissociated form, that is as the acetic acid itself. Only few will be converted into acetate by dissociating or by releasing the H plus. So therefore, by this we can call as acetic acid is a weak acid. Whether I am clear, all of you have understood? Any doubts in this? Okay. So Haga, with this particular background, any doubts you should ask, because now I am going to have a molecule where we can see the impact of inductive effect. Where we can see the impact of inductive effect. But whether all of you have understood whatever I have explained now, I told weak acid and strong acid and difference and why they are called as weak acid and why they are called as strong acid. Okay, so in that case, I will take a molecule. I will have a molecule where Cl, 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 COOH. Okay, so this molecule can also be written as CCl3, COOH. Anything is fine. Anything is fine. So this is where we have the trichloro. This is where we have the trichloroacetic acid. Trichloroacetic acid. TCA. Normally they will call it as TCA. When you go for the higher studies, or if you go to the research and all, they use this particular acid very often in their experiments. That's where we have the TCA, trichloroacetic acid. So it's acetic acid only, but instead of hydrogen, here it is chlorines which are attached. All of you got my point? Now this trichloroacetic acid, it will be dissociated. It will be dissociated as COO minus and H plus. So that means trichloroacetate. All of you got the point? Okay. So if you go back to earlier one, if I take acetic acid, 3 hydrogen, COOH, then it will be dissociated as acetate and H plus. So what is that difference between these two? What is that difference between these two? Anyone? What difference you can observe between these two? You can tell. What is that difference between these two you can observe? Direction. Okay. Yes, Bhumika. Direction. Why you have removed? Okay, wanted to tell it as arrow. Okay, fine. So we can see the arrow over here. So here it is single-sided. But here, small arrow, large arrow. That means acetic acid derivative, that is trichloroacetic acid, will be behaving as a very strong acid. They can behave as a very strong acid. They will behave as a very strong acid. But when it comes to acetic acid, it will behave as a weak acid. It will behave as a weak acid. What is happening here? Why trichloroacetic acid, which is a derivative of acetic acid, now it is behaving as a very strong acid. Okay? Even more stronger than that of the HCl and all. Very strong acid. But when it comes to acetic acid, it is a weak acid. So that's where we have the effect of the inductive effect. This is due to the inductive effect. Now, same molecule, I will write it here. So Cl, COOH. Okay, same molecule I have written here. Okay, carboxylic acid, one and all same. Here also it is carboxylic acid. Here also it is carboxylic acid. One and all same. Okay, na? Now, since three chlorines are present here, which will try to pull the electron, dipole moment, which will try to pull the electron towards itself. So that's where these three chlorine will do. So this particular carbon, poor fellow, it will be having a stress because these chlorine, they are pulling the electron away from this particular carbon. So due to that, it will approach the neighboring carbon. My dear friend, my electron has been pulled by these three chlorine. These three idiots, they are taking or they are pulling electron away from me. Please help me out. Okay? So therefore, it will start pulling the electron towards itself. This carbon, it will try to pull the electron towards itself. Now, like that, the chain will go on, and due to that, this bond will become weak. OH bond will become weak. So due to this pulling of electrons by these three chlorine, which has been transferred to this carbon, which has been transferred to this oxygen. Now due to that, this bond will become weak. So therefore, they will be easily dissociated as O minus H plus. All of you got my point? O minus H plus. So therefore, this is an example for inductive effect, where due to the presence of electron withdrawing groups, here chlorine is acting as a electron withdrawing groups. In resonance, chlorine will act as a electron donating groups. Please remember. But here in inductive effect, they will behave as a electron withdrawing groups. So due to the inductive effect, trichloroacetic acid will be a strong acid. So trichloroacetic acid is a strong acid compared to acetic acid. All of you got my point? So this is nothing but inductive effect, where electrons will be pulled towards or pulled by the electron withdrawing groups. So due to that, this pulling effect will be transferred from one sigma bond to another sigma bond. So there is the involvement of sigma bond, not like resonance where pi electrons are involved. Here it is sigma bond, sigma electrons are only involved. And finally, this OH bond will become weak. So this is called as inductive effect. Got my point? Okay. So that's where we have the one of the example. That's where we have the one of the example for inductive effect. Now I will take another example. Okay, I will not remove this. Okay, fine. I will write H. So H, COO minus H plus. Now I will write another molecule. Okay. What is this? Which is this molecule? Anyone? Which is that molecule? Down one, whatever I have written. You can write the IUPAC name for this particular molecule. You can write the IUPAC name for down molecule. Anyone has written? So this is trichloroacetic acid. This is acetic acid. I want IUPAC name for this. General one, we can write it as trimethyl acetic acid. Fine. But I don't want that one. I want IUPAC name. 2,2-dimethyl propanoic acid. Very good, Rohan. Very nice answer. So that's where it is 2,2-dimethyl propanoic acid. Very good answer. Propanoic acid. Right. Now, can you tell me, with respect to last category, where three methyl groups are attached to the carbon, which is next to the carboxyl group. Now, can you tell me whether it will act as a weak acid or a strong acid? Whether the last one, whether it will act as a weak acid or a strong acid. Anyone? So I will consider this one as the first example, this one as second one, and this one as third one. Now my question here is whether whatever a molecule I have taken, which is a third example, so 2,2-dimethyl propanoic acid, whether it will be behaving as a weak acid or a strong acid. Anyone? Any one of you can tell me? You can just mention weak or strong, that's all. Whether 2,2-dimethyl propanoic acid will be a weak acid or a strong acid. That's what the question here is. Okay, Rohan has written as weak acid. All of you will agree with him. He has written as weak acid. Yes. Yes, all of you are correct. It will be a very weak acid. It is weak acid even compared to acetic acid. Acetic acid can be a strong acid compared to this one. That is because, once again, due to inductive effect. Once again, due to inductive effect. Now, due to the presence of alkyl group, which is that alkyl group here? Methyl group. So, due to the presence of methyl group, so due to the presence of methyl group, and as we know, alkyl groups, they will act as electron donating groups. They will act as the electron donating group. Which one? Methyl or any alkyl group. So due to that, electrons will be pushed towards the carbon due to this oxygen. So that's where inductive effect will happen. So this bond will not become weak. This bond will not become weak. Instead, the dissociation of this will become difficult because O minus will not happen easily because it's already having electron which is coming towards it. So therefore, it will not release the hydrogen as H plus. It don't want any electron because already it is having more electron which is pushed towards this oxygen. So therefore, this molecule will be much more weaker acid even compared to acetic acid. Once again, inductive effect. In first case, inductive effect where electron withdrawing groups were there. In second case, it is electron donating groups. In both the cases, it is inductive effect. So why trichloroacetic acid is a very strong acid? Due to the inductive effect. So why 2,2-dimethyl propanoic acid is a very weak acid? Due to the inductive effect. Okay. So in this case, electron donating groups are present. In this case, electron withdrawing groups are present. Fine. So therefore, if I want to arrange, so trichloroacetic acid, it will be much stronger compared to acetic acid. It is much stronger acid compared to acetic acid, and it will be stronger compared to 2,2-dimethyl propanoic acid. Okay, so that's where we can write the decreasing order of the acidity. That's what we have the observation. So everything is due to inductive effect. Fine. Any doubts? Any doubts with regard to this one? So that's where we have the inductive effect. Okay, so I will remove these two. I'll keep trichloroacetic acid there. That's where we have the inductive effect. Okay, na? Any doubts? Whatever I have explained just now. Any doubts with regard to that one? If you have any doubts, you can ask. Okay. So in that case, I will write another molecule. Okay. I have taken the another molecule. Fine. Now this molecule I will write it as 3, 3, 3 trichloro propanoic acid. Trichloropropanoic acid. Okay, here we are mentioning the number because here another one methylene group is present. But here since only one carbon, another one is carboxyl carbon. So therefore trichloroacetic acid directly we have written. But here 3, 3, 3 trichloropropanoic acid. 1, 2, 3 numbering. Okay. Now what you can observe between trichloropropanoic acid and trichloroacetic acid? What is that observation you can make? What is that observation we can have? By seeing the reaction between trichloroacetic acid and 3, 3, 3 trichloropropanoic acid. Anyone? Whether? Okay, direction. Ashish is writing direction or arrow. Yes, absolutely fine. You are right. Okay. So in this case, I can see a bit it is coming backward. That means if I take this one as 2, I can tell that 1 will be a strong acid compared to 2. 1 is a strong acid compared to 2. What happened? Here also 3 chlorines are there. Like trichloroacetic acid, here also 3 chlorines are there. But still, why it has become a bit weak acid compared to TCA? Any one of you? So why it has become a bit weak acid compared to TCA? TCA is a very strong acid. But compared to that, this is a weak acid. Trichloropropanoic acid. What has made? Here also 3 chlorines are there, where we can see the electron withdrawing groups. Here also we have the electron withdrawing groups, right? But still it has become a weak acid, but it is a strong acid. What is that? Which is that one? Or what is that difference between these two? The difference here is, in this case, trichloroacetic acid, this carbon is directly attached to carboxyl carbon. But here, this carbon is attached to carboxyl carbon by the help of one methylene group. Yes, extra carbon. Yes. Or I can tell that here in first case, electron withdrawing groups containing carbon and carboxyl carbon, they are neighbors. But here, electron withdrawing carbon and carboxyl carbon, they are not neighbors. Okay, so they are not neighbors. Yes, CH2 is nothing but methylene group. So there is a presence of methylene group in between. So therefore, observe here carefully. Inductive effect, inductive effect will be decreased, will be decreased as the distance increases, as the distance increases. Okay, so that's where we have the inductive effect. As the distance increases, inductive effect is going to decrease. All of you got the point? So that's where we have the importance of the inductive effect and importance of the distance between this, in this case, carboxyl group and the carbon containing electron withdrawing groups. Carboxyl group and carbon containing electron withdrawing groups. As the distance increases, inductive effect is going to decrease. So therefore, acidic character is going to decrease, because OH bond will not be much affected as the distance increases. So inductive effect depends on the distance. Any doubts in this case? Any doubts? If you have any doubts, you can ask. Now I will go to the cyclic structure. This is with respect to non-cyclic molecule. I will go to cyclic structure. Okay, na? So for example, I have phenol. I have phenol. Okay, na? Anyway, these things in detail you are going to study in your second period. We have separate topic, alcohol, phenols and ethers. There you are going to study phenol, and I have ethanol. I have the ethanol. So in this case, among these two, both can be dissociated as O minus H plus CH3 CH2 O minus H plus. Okay, but if I want to go with the arrow, I can show like this. So this is where we have the condition. Okay. Now, in both the cases, due to the cleavage of OH bond, H plus will be released. Due to the cleavage of OH bond, H plus will be released and O minus will be formed. But among these two, phenol will be a strong acid. Among these two, phenols will be a strong acid, because whatever phenolate ion will be formed, this is nothing but phenoxide. Phenoxide, whatever phenoxide or phenoxide ion will be formed, they will be stabilized by resonance, or to be more appropriate, positive resonance. They will be stabilized by positive resonance, which will not happen with respect to ethanol. So therefore, phenol will be a strong acid compared to other alcohols. So therefore, it is called as carbonic acid. This is also called as carbonic acid. Okay, which one? Phenol. So why phenols are stronger acid? Because whatever products will be formed, they will be stabilized by the resonance. So due to that, the dissociation will be a bit easy compared to this one. But please remember, OH is not an acidic functional group. Okay, OH is not an acidic functional group, although they can dissociate H plus. That will happen under alkaline condition. Anyway, in detail we will not go, but for time being you can remember this one. That is the impact of the resonance. So what we will do is in tomorrow's class, we will discuss along with the resonance, if inductive effect is also there, what will happen to the property of the compound, or property of a given organic compound. Okay. Now you came to know what is the impact of the resonance with respect to the phenol. Why phenols they will be stronger acid compared to other alcohols. So the reason is due to the stabilization by the resonance. Okay. Anyway, tomorrow we are going to discuss inductive effect along with the resonance. What will happen? What will happen to the property of a element? Any doubt in today's class? Okay. Okay then. So I will stop here. Thank you. Thank you very much. Take care. Take care. Okay.